Let us discuss the second part of electrostatics, where we people are dealing with the concept of electric potential. In general, electric potential at a point, we define that one as the work done in bringing a unit positive charge or a test charge from infinity to the point of consideration. In fact, we all know the formula V is equal to the constant 1 by 4 pi epsilon naught Q by R. Basically, electric potential has got several applications. Let us now take up the important most concepts theoretically related to electric potential. Let us calculate electric potential at a point on the axis of a uniformly charged disk. Whenever we consider a uniformly charged disk, in the charged circular disk having surface charge density sigma, a circular strip of radius small r and width dr is considered such that the point P on the axis of the disk will be at a distance x from the center of the disk and root over r square plus x square distance from the circular strip. This is the general description one has to consider. Now let us consider this is the circular disk. Out of that, we have considered a small circular ring like. This thickness is dr, and of course we have taken up the radius is small r, total radius of the disk as capital R, distance to the point considered, that is P, from the center of the disk as x, and from the element considered here, the distance to the point P as root under r square plus x square. This is the general description regarding the disk. Let us now calculate what is the potential at that point P due to this element of thickness dr. dV is equal to 1 by 4 pi epsilon naught dq by root over r square plus x square. This formula gives us the potential at the point P due to the circular ring of small radius r with respect to the point P. Here dq is sigma into 2 pi r into dr. What actually is this concept? Every one of you can understand. Sigma is surface charge density, 2 pi r dr is the area. So sigma into 2 pi r dr, that is equal to charge on the circular strip. Whatever the strip we have considered here, the charge on the circular strip we now have calculated as dq is equal to sigma into 2 pi r into dr. Let us substitute this one in place of dq. Then what would be the value of dv? dv is equal to 1 by 4 pi epsilon naught sigma into 2 pi r dr whole divided by root over r square plus x square. This is the basic equation for dV when we consider surface charge density as a sigma and 2 pi r dr as the area of this circular strip what has been taken up over here. Now when we want the total potential of the entire disk, that means we can understand the V value is equal to integral between the limits 0 to capital R being the radius of the entire disk, it is dV, integral between 0 to R dV. What will be its value now? Sigma by 2 epsilon naught integral between 0 to R dr by root over r square plus x square. If you simplify this whole lot, you will be getting the formula V is equal to sigma by 2 epsilon naught into root under r square plus x square, this time r being the total radius of that disk, minus x. This is the final formula for the potential at the point P due to the entire disk what has been taken of radius capital R and having surface charge density sigma. Now, if you consider few special cases of this disk, let us take the very first case. At the center of the disk, what would be the electric potential? If they ask you this type of a question, at the center of the disk, x value will be 0. By keeping x value 0, by putting its value here, you are left with V is equal to sigma capital R by 2 epsilon naught. This is the formula for electric potential at the center of the disk. Similarly, they may ask you a special condition like this. If x is greater than capital R, what is this x over here in fact? It is the distance to the point of consideration. That value of x, if it is many a number of times greater than the total radius of the disk, then what happens to this value of root of r square plus x square? That now can be rewritten as x under root 1 plus r square by x square. In other words, you can even write the same thing as x into 1 plus r square by x square whole power half. Now, applying binomial expansion, that we can write it like this as x into 1 plus r square by 2x square. This even can be rewritten as x plus capital R square by 2x. Now, if you just take this equation in place of root over r square plus x square, now you can substitute the value of V, which is equal to sigma by 2 epsilon naught into x plus r square by 2x minus x. How much it now becomes simply? This x getting cancelled over there, you are left with sigma capital R square by 4 epsilon naught x. This is the outcome. This in fact is going to give us the electric potential at the point P when the distance to the point which is taken as x is many a number of times greater when comparing to the radius of that disk as such. From this particular equation, if you substitute the formula for sigma as q by pi r square, we get V is equal to 1 by 4 pi epsilon naught q by x. This is going to be the final formula for electric potential, one should remember. In the same manner, they may ask you to calculate electric potential on the edge of the disk. This is the disk what is considered. On the edge of the disk, you imagine a point P here. This being the center, this being the radius. Let us consider this angle as theta, and this distance to the center from the point P is the radius of that particular disk as such. Now, to calculate the potential at the point P on the edge of a circular disk of radius capital R, let us divide the disk into several rings with P as the center. Keeping the point P as the center, imagine several rings like this on the disk such that we can easily calculate the value of potential at the point P that is considered at the edge. Now check the calculation carefully. The potential due to one segment between small r and small r plus dr. In between these two values, what is the potential? Let us write that formula. dV is equal to the constant 1 by 4 pi epsilon naught into dq by r. But what is this dq over here? It is the value of charge on that circular ring what has been imagined, that now can be written as sigma, which is surface charge density into area of the ring. What would be this area of the ring now? It will be 2r into theta into dr. In fact, it is 2 theta into r. That only we are writing 2r into theta dr. So what would be the value of dq now? Sigma times 2r theta dr. That value you substitute in place of dq here. Then what would you get? dv is equal to 1 by 4 pi epsilon naught sigma into 2r theta dr divided by small r. If you simplify this one further, sigma by 2 pi epsilon naught theta dr is equal to dv we get. But in this particular equation, we know pretty well what is the formula for small r. Small r will be 2r cos theta. When small r is 2r cos theta, what would be its differential value? dr becomes minus 2r sin theta d theta. This value in place of dr you substitute now. Then what would you get? You check it. dv is equal to sigma by 2 pi epsilon naught multiplied by minus 2r sin theta d theta. That in fact we can rewrite that one as sigma r by pi epsilon naught multiplied by theta sin theta d theta. But when we want the complete potential due to the total system, we can integrate this dv between the limits pi by 2 and 0. So what exactly is the concept here? V is equal to integral between the limits pi by 2 to 0 dv. What would be its formula now? Sigma capital R by pi epsilon naught integral between pi by 2 to 0 theta sin theta d theta. That of course if you simplify the total lot, you will be getting the potential V is equal to sigma capital R by pi epsilon naught. That is the outcome which in fact is giving us the potential at the point P as such. Equation. Let us calculate electric potential due to a solid sphere of charge at a point inside the sphere. The sphere what has been considered here is supposed to be charged uniformly. And the point of consideration where we are going to calculate the potential, that point should lie inside the sphere. That is actually what we just want. We know the electric intensity at a point P, which is at a distance small r from the center of a charged sphere of radius r, as E is equal to 1 by 4 pi epsilon naught small q small r by capital R cube. What is capital R here representing? It is the radius of the entire sphere. And what is the small r representing here? It is the distance to the point inside the sphere what has been considered. So when we want the corresponding potential dV, it can be written as minus E dr, because we know very well E can be written as minus dV by dr. That is the usual formula, wherefrom we can write dV is equal to minus E dr. And what is the value of E? You just substitute this value in place of this. So this now becomes minus q by 4 pi epsilon naught small r dr divided by r cube. This r cube is capital R cube, which of course is the radius of the sphere. Now when we want the potential at that point inside the sphere, we have to integrate that one between the limits Vs to V. That of course V on the surface to the point where we are considering the potential as V. So observe this integration carefully. It is integral between potential on the surface to the potential at the point dV. That now can be rewritten as minus q by 4 pi epsilon naught capital R cube integral between capital R to small r, r dr. What is this capital R now? It is the radius of the entire sphere. And what is this small r now? It is the radius or the distance to that point what has been considered inside the sphere. If you simplify this one, you get V minus Vs, that is potential at the point minus potential on the surface of the sphere, is equal to 1 by 4 pi epsilon naught q by capital R cube into r square by 2, that is integral value between the limits capital R to small r. That is actually the equation. If you simplify that one further, here potential on the surface of the sphere Vs is equal to 1 by 4 pi epsilon naught into q by r. That is the actual equation for the potential on the surface of a sphere of radius r which is charged to q. Then what would be the potential at that point P, what is considered inside the sphere which is at a distance small r from the center? That V now becomes 1 by 4 pi epsilon naught q by capital R multiplied by 3 by 2 minus half small r square by capital R square. This particular equation for the potential at a point inside the sphere is one of the very important aspects for us at JEE. So if you take this formula, we can even discuss few special cases on this formula. Let us start from the first case as such. First case says, at the center of the sphere, what would be the potential? At the center of the sphere means we can understand well from this formula, this value of small r now becomes 0. Small r is the distance to the point considered from the center of the sphere. When the center itself is the point of consideration, r automatically becomes 0. When small r becomes 0, substituting that value here in the above equation, we get V at the center, that is electric potential at the center of the sphere, now becomes 3 by 2 times 1 by 4 pi epsilon naught into q by r. Now if you look at carefully, 1 by 4 pi epsilon naught into q by r is the formula for potential at any point on the surface of the sphere. Therefore, what can we rewrite this one as? 3 by 2 times potential at the surface. That in the sense potential at any point on the surface of the sphere. So what you can conclude from this equation, please? Potential at the center is equal to 3 by 2 times the potential at any point on its surface. So 3 by 2 means nothing other than 1.5. Therefore, we can rewrite the same this way. Electric potential at the center of the sphere is 1.5 times the potential at the surface of the sphere. That means at the surface means at any point on the surface, the distance is going to be equal to the radius of the sphere itself. So this is one area one has to concentrate on. Now let us consider few more important cases related to the formula given above. Important cases of charged spherical surfaces. Let us start from the first one. What is the potential at O? We have here three separate spheres. Let us consider them as A, B and C, having radii RA, RB and RC. The charge on the first sphere is QA, charge on the second is QB, charge on the third is QC. This is the sphere which we people have considered. Now from this one, they can ask you different cases. This is the center O. So the first question what they can ask you is, what is the electric potential at O? Electric potential at O, if you just want to know here, you are having three different charges which are influencing that point O. Therefore, all the three charges, they cause three potentials at the point O. So what you need to calculate here is, calculate the potentials due to QA, QB and QC, then add them all. Then what would be the equation you are going to get now? You check it. Potential at O is nothing other than VO, which is 1 by 4 pi epsilon naught into QA by RA, charge on the first sphere by radius of the first sphere, plus QB by RB, charge on the second sphere by radius of the second sphere, plus QC by RC, charge on the third sphere by radius of the third sphere. So what would be the potential at the center, that is at the point O? If at all they ask you, direct formula you can write by taking VO as 1 by 4 pi epsilon naught QA by RA plus QB by RB plus QC by RC. This is one of the important most applications what we have. Similarly, they can ask you what is the potential at any point on the surface of this first sphere A. This is the smallest sphere out of the three. You can understand its radius is RA. You can understand the charge on that sphere is QA. Then what would be the potential on the surface of the first sphere A? It is VA, we call it. 1 by 4 pi epsilon naught into. So what you should understand now, when a point is considered on the sphere A, for sphere B and sphere C, the point lies inside. Whereas for sphere A, the point lies on its surface. So once again you will be coming across three potentials over there. One on the surface of the first sphere. Second one inside the second sphere B. Third one inside the third sphere C. So when you calculate these three, what would be the formula? VA is equal to 1 by 4 pi epsilon naught, that is a constant K, into QA by RA plus QB by RB plus QC by RC. So what you should understand here is whether the potential at the center or the potential on the surface of A, whatever they ask, the result will be the same. So this is the formula one should recollect and remember as the potential at any point on the surface of the smallest sphere of radius RA having charge as QA on it. Now come to the third case. What would be the potential at B? Potential at B means what you know? It is the potential at any point on B. When you talk about a point on the surface of the second sphere B, that point lies inside the third sphere and it lies on the surface of the second sphere and it will be outside the first sphere. I repeat once again, the point when we consider on this sphere B, it lies outside the first sphere A, inside the third sphere C, and on the surface of the second sphere B. Therefore, what would be the potential on the surface of B? It is VB is equal to 1 by 4 pi epsilon naught QA by RB plus QB by RB plus QC by RC. This is the formula one should remember as far as potential at any point on B that is concerned. Now come to the last case in this. What would be the potential on the outermost sphere, that is C? When you take the point right on the surface of C, it will be on the surface of C, it will be outside B, it will even be outside A. For A and B spheres, the point now lies outside. For the sphere C, it lies right on its surface. Due to which, what would be the formula now? VC is equal to 1 by 4 pi epsilon naught into QA by RC plus QB by RC plus QC by RC. If at all you want to take RC as common here in the denominator, this now becomes 1 by 4 pi epsilon naught QA plus QB plus QC whole divided by RC. Like that also we can write. Next case. A charge Q is distributed uniformly on the surface of a sphere of radius capital R. You can check, this is the surface having radius capital R, this is the sphere, right? And it is covered by a concentric hollow conducting sphere of radius 2r. This is actually a sphere of radius capital R having a charge plus Q. This sphere now is covered by one more spherical shell. What is that conducting sphere, hollow sphere's radius? It is given 2r. Very clearly it has been mentioned here, right? The outer shell now is connected to the earth. In fact, one can understand directly, whenever a surface is connected to the earth, the potential on that particular surface at every point becomes 0. That is the understanding one need to have. Now the questions they may ask you are like this. The very first question: what would be the charge on the inner surface of the hollow sphere? Now you can write the answer straight away. This is the sphere of radius capital R. This is the sphere of radius 2r. Charge on the inner sphere is plus Q. Then what happens? Inner surface of the outer sphere will now be induced with a charge minus Q, and outer surface will now have a charge Q dash. Now the question is, what is the charge on the inner surface of the hollow sphere? Very clearly you can say it is minus Q. That is the observation. Now the second point, the charge on the outer surface of the hollow sphere. In true sense, when the outer surface is directly connected to the earth, I have already given you that condition earlier. If it is connected to the earth, the charge on the surface becomes 0 automatically. That only we can explain it like this. When the outer surface is earthed, its potential should be 0. But what would be the potential here now? V is equal to 1 by 4 pi epsilon naught into Q by 2r, that is due to the charge plus Q, minus Q by 2r, that is due to the charge on the inner surface of the outer sphere minus Q, plus Q dash by 2r, that is the charge on the outer surface of the bigger sphere. That total value now should be 0, because potential should be 0 when it is earthed. We know that one very well. Thereby you can get once again here Q dash is equal to 0. So what is your conclusion? There will be no charge on the outer surface of the hollow sphere. That is the concept one should understand from this one. What is the next question here? 3 concentric spherical shells A, B and C are of radii capital R, 2r and 3r. Look at here, there is a small spherical shell of radius capital R here. Above that one, of course, covering that one, we have another spherical shell of radius 2r. Over and above these two, there is one more spherical shell of radius 3r. Now the point here is B is earthed. That means the second spherical shell, the middle one, is now connected to the earth. And A and C are given charges Q and 2Q respectively. The charge on A is now plus Q. The charge on this C, the outermost spherical shell, that is given as 2Q. Now, what would be the distribution of charge, they may ask you. Like, see, what is the charge inside A? We in fact know pretty well charge lies only on the outer surface of the spherical shell. Therefore, what would be the charge inside A now? It will be 0. So, no calculation that is needed for that. Second bit, charge on the outer surface A is how much? It has been given positive charge Q. So naturally, what we can understand, the charge on the outer surface of the innermost spherical shell, that is A, that now becomes plus Q. So you can understand, charge on the outer surface of A is now going to be plus Q. Now come to the third bit. Charge on the inner surface of B is how much? B, of course, is earthed. Outer surface is connected to the earth, not the inner surface. Therefore, due to induction, minus Q charge comes onto the inner surface of the second sphere. So, what you can understand now? Charge on the inner surface B now becomes minus Q. That is the question they may ask you. Come to the fourth bit. What would be the charge on the outer surface of B? Outer surface of B now can be taken as plus Q dash. The charge on the outer surface B of B is now plus Q dash. But you all know that B is earthed. So what we should write? Since B is earthed, its potential is 0. The potential on the surface should be 0. That means VB should be 0. VB 0 means, what is the equation for that? 1 by 4 pi epsilon naught into Q by 2R minus Q by 2R plus Q dash by 2R minus Q dash by 3R plus 2Q plus Q dash by 3R. Now you can understand these two are due to first and second spheres, these three values. These two are due to the third sphere. Sphere in the sense spherical shell. This total is going to be 0 because VB should be 0 when it is earthed. Then what should be the value of Q dash is the question. What is the value? If you simplify this total lot, you get Q dash is equal to minus 4Q by 3. This is the formula for calculating the potential on the surface of B. Since it is earthed, it should be equated to 0. The moment you equate that one to 0, you will be able to get what is the charge on its surface right now. That is Q dash is equal to minus 4Q by 3. Let us take the next bit now. What would be the charge on the inner surface of C? C means the outermost spherical shell. That now can be taken as minus Q dash. What is Q dash? Already we people have discussed earlier. Q dash is minus 4Q by 3. That value now is to be substituted here. Minus of minus 4Q by 3. Minus of minus becomes plus. Then it becomes 4Q by 3 as such. So that is the charge on the inner surface of the outermost spherical shell C. What is the next bit they can ask you? Charge on the outer surface will be how much? When I consider the charge on the outer surface, it now should become 2Q plus Q dash. Already the charge on C is 2q. Plus this is the additional charge q dash. So what we can write? 2q minus 4q by 3. How much it is now going to be? 6q minus 4q, that means 2q divided by 3. So what would be the charge on the outer surface of the spherical shell C? That is nothing other than 2q by 3.